Today, which is Henrik Johansson, who's going to talk about the titles on the board.
Thank you. So first of all, I'd like to start with thanking the organizers for letting me speak here, and also thanking the Institute for inviting me. Okay, so I'm going to talk about this interesting structure, which is makes an appearance in the scattering amplitudes of generic gauge theories and gravity theories, and I will refer to it as color and kinematics duality, or duality between color and kinematics, and my title is just a variation of that. So in scattering amplitudes, there is basically two important ingredients, and that's the dependence on color and the dependence on kinematics. And they are usually treated in a very different manner. Well, we say that color is trivial, and we say that kinematic dependence is very difficult, or very different, and this is the interesting part. So you usually separate them, but what we noticed, which goes back to this paper here, with Byrne, Carrasco, and me, back 2008, what you notice that if you treat them on a very similar footing, then you notice that there are some remarkable similarities, and this is what we refer to the duality. Okay, so let me start with the outline of this talk. So basically, I will have three parts of this talk. So first will be a review of tree level. So I apologize to those who heard this talk before. There will be quite basic stuff in this talk, so I apologize for that. But I hope to those who are not familiar with this to get a good flavor of what this means. Okay, so then I'm going to talk about something which is a bit new, and most of it is actually not going to be work by me, but I'd like to talk about it anyhow. So there's some novel manifestations of color and kinematics duality. So I'm just going to mention it, or I'm going to have talk about it for 10 minutes or so. And then the third part of my talk is going to be on one loop and two loop representations of this amplitude which satisfy this duality. And so in part I'm going to display how they look like, and also in part I'm going to sketch out how the calculation was done, so you can get a good flavor of how to do these things. Okay, but before I get into details, let me try to summarize in a few words what the color kinematics duality stands for. I don't know if this is readable. Maybe it's too small. I'll try to write a bit bigger. Okay, so well, this is a working definition. So it's this is the current one. So basically, the way I like to think about it is that the kinematic numerators of scattering amplitudes satisfies the same general algebraic relations as color factors or properties. So in a minute I'm going to explain exactly what numerators and color factors are, but just take it as the building blocks of the amplitude. So I'm going to talk about scattering amplitudes because that's the examples we know of. And other important word here is that that it's only for general properties, not for specific. So not properties which depends on the specific gauge group of the color factors and so on, but more general properties that you should equate on these two different objects. So let us look at an example at tree level. So let's look at super Yang-Mills, or let's put super in parentheses. At tree level. So I'm going to write the amplitude is I'm going to write up the color-dressed amplitude, so it's going to be curly A, and it has m point 3. So it's a sum over diagrams, and I'm going to make the diagrams cubic. And so there's two ingredients which is important: the numerator, the color factor, and then also the denominator factor, which is goes along for the diagram. So this is, first of all, the denominator is just the Feynman propagators. And this is the color factor. And this is this is whatever remains, so this is the kinematic numerator. Okay, so this is the way we like to represent, or this is the way we like to think of our amplitudes, and this way of treating them at tree level. And now the duality is basically that these two objects satisfy the same general properties, C and N, so let's say same general properties. So. Right. So try to represent an amplitude tree level using this representation, such that the algebraic properties of these two objects are very similar. So that's the goal. So first of all, what are the color factors? If you're talking about Yang-Mills at tree level, then you can pick, you can construct all your color factors using FABCs, for example. So it's going to look something like this. It's going to be a string of FABCs. And so on. Right. So that's basically how they're going to look like, and we can represent this by a diagram to simplify the notation. So we can skip all the indices. So typically you can write something like this. This is just one diagram, and there's of course many other diagrams. They don't have to be on this form. They can be branching off in many different directions. But it looks like this, and there is indices, and there's something like this, and so on. So that's the diagrammatic representation. Now, what's the numerator? Well, if you happen to compute the numerator, say using ordinary Feynman diagram, then the numerator will look something like this. There will be a polarization tensor, for example, dotted into a momentum, and then there will be, say, another polarization tensor dotted into a third polarization tensor. And so on, momentum dotted into another momentum, and so on, as much as you can think of. So it's actually quite a mess here in general. That's what we know from using Feynman diagrams, is that you get a lot of such things, and they're quite messy. So again, in order to simplify the notation, we're just going to denote this. Maybe I should getting kind of small here. So we're just going to denote such things. by some kind of diagram like this. And well, it's not clear how you should compute these diagrams in the same way that you know how to compute color factors, but it's clear that there is diagrams in this representation and they have poles. So you identify the numerators with the poles that you see in this diagram. So there's some states here, and just let me denote them schematically by A, B, for example, and so on. This states, well, this just contain all the states, particles, information, and so on, and kinematics, for example. Okay, one thing you might wonder about this representation is, well, since I want to have my kinematic numerators have the same general properties, and since this is the color is given by cubic diagrams, then I also have the kinematics. Well, that's one of the properties that I like, to have diagrams which have cubic diagrams. So the question is, what happened to the diagrams which are not cubic? So we know in Yang-Mills theories that there are diagrams which are quartic, right, in the Feynman diagram. So what happens to these guys? Well, basically they're trivially removed by just multiplying by 1, and 1 is s over s, for example. So after you multiply by this, what you can do is you can say, well, let me denote this diagram implicitly having this propagator and then putting a numerator in front like that. Well, so in this talk, I'm going to actually draw several different diagrams, and sometimes the diagrams represent color, and sometimes they represent kinematics, and sometimes they represent color and kinematics and propagators all together. So bear in mind they might be a bit confusing, but here in this case the propagator is actually included in this diagram. So this is kind of trivial. Whenever you see a contact diagram, you just multiply by s over s, or t over t, or u over u, and then you get something which is cubic, and then you have a numerator factor instead. So that way you can impose the duality in 3 steps. So first step was to use cubic diagrams. Second step is to actually, so this is to remove the quartic vertices. Second step is to actually study what are the properties of these color factors. Well, for example, one property is that if you exchange A and B of this color factor, you get the same color factor back, but with a minus sign. So let me just write it like this. So AB, where I suppress all the other indices, is equal to minus CBA, right? So that's one property, which is the generic property of any Lie algebra. So if we want kinematics to satisfy the same general properties, it should also satisfy this. So you want something that looks like this schematically, that when you write up the numerator and then you interchange the states, all states or all quantum numbers simultaneously, you should pick up a minus sign. Now you might wonder, is this true? Well, it's kind of trivial actually, because the full amplitude has to be invariant when you interchange all the particle, well, when you interchange 2 labels, or when you interchange all the quantum numbers of 2 particles, because the full amplitude is both symmetric. So that means that the combination Ci, Ni, it better be invariant under this, so it has to go back to itself, which it achieves by simply flipping this one and flipping this one simultaneously. Another way to see it is if you just look at the Feynman rules, for example, at the cubic vertex in gauge theory, it's obvious that it has this property. So these 2 properties are more or less trivial. The really non-trivial property is the third one, which is the fact that these objects belongs to a Lie algebra, so they satisfy relations that we know of as Jacobi relations, right? So that's Jacobi relations. So schematically it's always of the form ff plus ff plus ff is equal to 0. I'm not going to write out the indices. But of course this could be multiplied by some other f and so on. And you can have multiple f's here on the outside. So in terms of this language of the color factors, it's going to be that there's the ci plus cj plus ck is equal to 0. So there's a triplet of color factors which has to add up to 0. Now sometimes sometimes I might change the sign because the sign is intrinsically ambiguous. So sometimes accidentally I might write down a negative sign. So let me just denote it like this. So this means that there's always triplets of color diagrams such that when you add them up with appropriate signs, you get 0. So this is the essential property of these color factors. So now to make the duality between the kinematic numerators and the color factors manifest, you have to do the same thing for these guys. So this is equal to 0. So now, even though the sign is somewhat ambiguous, you have to pick the same sign here as here. And then, if you do that, then you have enforced that they have the same general properties. Okay, so far it's been a bit abstract, so let me show you an example. So let me show you the 4-point. Well, it's supposed to be a color rest amplitude, so the 4.3. So in this case, we have 3 different diagrams. So we have an S-channel diagram, and we have a T-channel diagram, and then we have a U-channel diagram, like that, or diagrammatically, like this, right? Plus this guy, plus the cross channel, this guy. Okay, so now we want to check if, for example, ns plus nt plus nu is equal to 0, because that is the only Jacobi relation you can write down. I didn't. Okay, so maybe I should draw here what the Jacobi relation is diagrammatically. So, for example, you can draw this cross diagram equal to the T-channel minus the S-channel. So this convention of drawing it is that I look at cyclic ordering and the way I draw it, and I write down the FABCs accordingly. And if you do that, then you get these sign conventions. Okay, so this relation is something I would like to check, and well, maybe I should write it slightly different here, but well, let me write this a minus sign there. So we want to check whether there is such a relation between these 3 quantities, ns, nt, and u, for super Yang-Mills, or Yang-Mills for that matter, at 3-level 4-point. But there is a line 1 problem, and that is that, well, these numerators are not supposed to be gauge invariant, right? Because if, for example, you compute them using Feynman diagrams, Feynman rules, you know that individual Feynman diagrams depend on the gauge choice. So on line 1, there is a problem. We have a relation between objects which are not strictly well defined. So what do? Well, you could close your eyes and try it anyhow. So if you do that, it turns out by good fortune that if you use Feynman diagram, this relation is true. And just for the sake of to be definite, let me put this plus sign instead. So so you compute this object with using Feynman diagrams, and you check. Indeed, there is such a relation. So this turns out that at 4-point, by good fortune, the relation doesn't really depend on the gauge choice. This happens to be a gauge invariant combination. But as you go to higher points, as you go to 5 points and 6 points and so on, this is no longer true. So then you get yourself into some trouble. But then the question still arises, is this relation, does this relation somehow constrain the theory in any way, or is it just constraining things which are not physical? And to do that, what you have to do is you have to translate to gauge invariant variables. Variables or quantities. Okay, so what are the gauge invariant quantities which enter a 4-point 3 amplitude, color risk 3 amplitude? Well, it's really the color ordered amplitudes. So they're color ordered. Or color stripped trees. So for example, this one, 1, 2, 3, 4, and if you write it down using these variables or these numerators, you can work out that there's a S-channel diagram, and it comes out to be minus the T-channel diagram, and that just happens because of the various sign conventions. And similarly, there's another tree which is 1, 2, 4, 3, for example, this color order, which is a different independent color order, and this is equal to NU over U minus NT, NS over S. So the color ordered amplitudes only have 2 poles. Because they're effectively planar, so they cannot have the third pole, which is non-planar. Okay, so that's the third amplitude you can write down, and that's 1, 3, 2, 4, which is equal to NT over T minus NU over U. Now you can try to write down other orderings as well, but because this is cyclic, you can always put, for example, leg 1 at the first location, and similarly, there's a symmetry when you reverse the order here. So this basically comes down to there's only 3 different objects that can write down, 3 different objects. So now it looks good. We have 3 unknown numerators, and we have 3 equations relating it to 3 gauge invariant quantities. So it naively looks good. I won't write down exactly what they are, but you can just compute them using Feynman diagrams, for example. But that depends on which gauge you pick, or which. Well, I mean, whether you pick light cone gauge or whatever. Oh, yeah. So we're gonna solve it in a second. Yeah. Okay. Sorry. Yeah. So the goal is not to write down this form of numerators, but in this step, its goal is actually just to invert the system. And as I said, naively, it looks like you have 3 variables, you have 3 equations, so you can invert it. But if you actually look closer, it doesn't work, because if you add up all 3 amplitudes, then you get 0. Okay, like this. This is 0, and this is obvious here because you see that this one is here, and this here again with a negative sign. This one is here, and this here again with opposite sign. And this one is there, and they also opposite sign. So just writing it like this, it manifests that you get this sum to be 0, and that's actually a known identity. This, for example, is called photon decoupling. This is called photon decoupling relation, or it's also called Claes-Coif relations. So this is the simplest instance of a Claes-Coif relation. Okay, so that really means that this really means that we have three variables and we have two equations. So because this one is redundant, for example. So now to invert the system, you really have to pick some. Well, either you have to solve it in terms of a free parameter, or you have to pick a gauge. You have to make a gauge choice. Where when I say gauge choice, I don't really mean gauge choice in the usual sense, but really I make a choice for what one parameter should be. Okay, so for example, let me pick ns to be equal to 0, which is kind of a strange choice because that looks like it removes a pole in the amplitude. But in fact, what happens is that the other numerators actually absorb this pole indirectly. So the numerators, even though I call them numerators, doesn't have to be strictly local. Okay, so what happens if I do this choice? Well, then we can invert. The numerators. So we get that nt is equal to a1, 2, 3, 4 times t, the minus sign, and we get that nu is equal to a1, 2, 4, 3 times u. Okay, so now we have achieved what I said. We have converted to gauge invariant quantities, and now we can check whether this identity actually means something. So we just plug it in, and in this case, since ns is 0, we can cross this out. So what we should compute is just the sum nt plus nu, which should be equal to 0. So it's, well, minus a1, 2, 3, 4, t plus a1, 2, 4, 3, u. So this is 0. Well, if this was meaningful at all, this representation, then this should be true. But okay, how do we know that? Well, you can check it. Well, let me first, okay, so let me actually write down an example what these amplitudes are. So if you're in, let's think of a pure QCD amplitude, or for gluon amplitude with felicity minus minus plus plus. Then this take a particular form. Well, you can use the Park-Taylor formula, but at 4 point there's another formula which you can write down, which looks like this: 1, 2 squared, and then 3, 4 squared over s and t. Okay, so let me write down this one instead. So this one has the same numerator actually, or this numerator here, but the denominator is slightly different. Instead of having s and t, it has s and u. And yeah, so now you can see what happens is that this factor here actually cancels this factor here, and this factor here cancels that factor, and then it just says that whatever remains, sorry, this factor cancels this factor, so then this numerator over s is equal. So that's what the equation says. So that's very good. So that just shows that, first of all, what we started to write down makes sense, And second of all, it means that you get even though it looks like you were working with objects which are not well defined, so it looks like you relaxed relaxed the need to use gauge invariant quantities when you wrote out the amplitude. In the end of the day, you get something which is quite strong. You get something which is stronger. Well, you get relations between gauge invariant quantities, which is something that doesn't follow from gauge invariance itself. So that's quite interesting. Okay, so this is how it works at 4 points, but it turns out if you do higher points, as we did in this paper from 2008, the story is essentially the same. Again, you write down a representation which has a certain number of cubic diagrams. You start checking whether the Jacobi relations hold, and in this case, at 5 points or higher points, they don't. But if you translate into gauge invariant quantities, which are the trees themselves, the color ordered trees, and you solve this system, which is a system which naively doesn't have an inversion, but you do it anyhow by picking some gauge choices, for example, or leaving them as free parameters. And then at the end of the day, when you plug back the solution into this equation, it means something very physical, which it means a relation between gauge invariant quantities. So that shows that this formalism, which looks a bit strange from the beginning, it actually imposes quite strong constraints on amplitude. Well, at 4 point level, you only get one constraint, but as you go to endpoints or m points, you get the factorial growth of the number of constraints. And in the end of the day, the number of independent amplitudes that you get is this well-known number n minus 3 factorial, which is the same number that feature, for example, in string theory. And you also, of course, I didn't emphasize that, but you also reproduce the Kleist-Coif relations. The Kleist-Coif relations essentially just follows because there's a sign flip. There's a sign flip here on the second property, and that's actually what makes the Kleist-Coif relations happen. But the Jacobi relations here, they're really responsible for this sort of relations, which involves Mannestam invariance. And altogether, the Kleist-Coif relations and this relations, which are called BCA relations, they reduce the number of independent amplitudes to be n minus 3 factorial. Yeah.
You said for 5 points?
Yeah.
In which sense it doesn't work? If I write the 5 point result as cubic diagrams extension?
It doesn't work for Feynman rules. So if you pick your favorite Feynman rules and favorite gauge, it doesn't work.
So it means the numerator has to be put in a special form.
Yeah, it means that's not the right Lagrangian, or that's not the right Feynman rules for these objects. But it doesn't mean that the theory itself, the theory admits this representation. So it just means that you have to massage your Feynman rules, or you have to massage the Lagrangian such that it reproduces this. And this actually has been done. It has been done by Yutin Huang in the audience. They actually did this. They took the Lagrangian and they massaged it by adding 0. And at the end of the day, they got this to work out for 5 point. Okay, so this number, as I said, this is quite familiar, and this is the number which, if you do string theory calculation, this is the number of vertex operators that you have to integrate over. And indeed, after we published this paper, there was some work in string theory which reproduced this relation, and that was by Björn Bohr, Darmgaard, and Van Hove, and Stefan Stieberger independently. So they found these relations, and this, what they call this relation is monodromy relations, because they are related to the monodromy when you integrate on the world sheet. And they get the same relations, except that these objects here turns into well, either sines or exponentials, but otherwise it's they're quite similar. So So that shows. So that actually was the first proof that these relations exist, that these relations exist to endpoints. We checked it up to 8 points originally. Okay, so that's really the first curious observation that something is going on here, which is quite interesting, and which we yet have to fully understand. We don't fully understand it yet, I should say. But okay, what's the second curious observation? And let's see. Yeah, let me go over here. Okay, let me just erase this section. Well, so it turns out that something very unexpected happens when you try to organize Yang-Mills theory in this way, and that's by some accident you also happen to reorganize gravity. So that we have the amplitude. Let me write it down again, which is over there in Yang-Mills at tree level. And it looked like sum over diagrams and some kinematic numerator and color factor and some denominator, which is just Feynman propagators. This is cubic. So now, since we postulate that this object satisfies the same general relations as this object, you can imagine the possibility. What happens if you take two copies of the same object instead of having this cross term between n and c? What happens if you take n times n? So let's do that. So let's take an n and let's take another n and divide by the denominator. What is that thing? It turns out that this is gravity. For some, quite miraculously, because when we started doing these games, we didn't have in mind anything with gravity. But in the end of the day, we got something which is very, very clean in the setting of gravity. So this is what we call gravity double copy. And I should say this is actually not this formula was not known, but there's another formula which is well known, and that's KLT, Quayle-Llewellyn tie relation. And Quayle-Llewellyn tie relation is a relation between gauge invariant partial tree amplitudes, which then gives you gravity amplitudes, and this was originally proven in string theory, but there's a field theory equivalent statement of it. And so what happens here is that this formula is actually equivalent to KLT at tree level. But curiously, KLT doesn't have a well-defined equivalent formulation at loop level, but it turns out that this one has. So that's one reason why we were excited about that. I should also say in a parenthesis here that sometimes when I discuss this, people ask me what happens if you take two colors instead of two color factors instead of kinematics. So you take something which is Ci, Cj over denominator, and we can put a tilde there because they don't have to be same. And well, it's some sort of scalar theory. And I don't know much about it, but certainly it does exist. For example, you can even write down the Lagrangian of an example. So it's just the interaction. So it's a trace of three scalars where you have a commutator. So that's certainly something you can write down. In fact, I think it was Yutin Huang who told me that this is a simple case. So this exists. Okay, that's all I want to say. Okay, now let me go back to the gravity case. So just like in KLT, you can construct different kinds of gravity using this formula. So this numerator doesn't have to be the same. It can be two different kinematical numerators, which corresponds to either two different theories, but also you can think of it as being different external states and so on. So, for example, just to demonstrate the power of constructing different theories using either this or using KLT. So let's consider some cases. So here is the numerator, here is the n tilde numerator, and here's the product. So if you take, say, n equals 4 super Yang-Mills on one side, and then you take n equals 4 super Yang-Mills on the other side as well. So this is actually a square. Then what you get is n equals 8 supergravity. And this is well known in the string theory setting and KLT setting and so on. But we can actually do this at loop level, which I will briefly mention in a few minutes. Okay, so another case, for example, which is interesting, is that if you take n equals 4 again, and then you take n equals 0, which is also known as QCD, pure QCD, then you get n equals 4 sugra. And in fact, I think a month and a half ago, there was this impressive calculation by Yutin Huang and collaborators, where they computed 3-loop n equals 4 supergravity using this prescription and using this formula to show that there was no divergence. So this shows that it's very useful. Okay, a last example is if you pick n equals 0 on both sides. So let me just write Yang-Mills. Then you get something which is non-supersymmetric. So in fact you get Einstein gravity. Plus some extra states which are dilaton and axion. You have to have this because, for example, in 4 dimensions, there's 2 states here and there's 2 states here for the free particle. But here, so 2 times 2 clearly has to be 4. So there's 2 states here and then there's 2 extra states. But it's likely that if you have a suitable projection, you can remove these states. Although it hasn't been demonstrated, but it's quite possible. Okay, okay. So that was basically the 3-level review. But before I go to loop level, let me show you some new interesting developments. So, so there was this work about a month ago by people at Albert Einstein Institute in Golm and also from Uppsala, and this is work by Aguirre, Song Hee, and McLaughlin. So what they did is that they looked at the Bagger-Lambert Gustafson theory and checked whether there is a similar color kinematics duality there. And the answer is well, let me just review a little bit. We heard about it earlier, or this morning, by Arthur, but so there's this tree algebra. And this tree algebra is related to the structure constant of this, this equivalent. Let me just write it down. Okay, so there's this tree algebra structure which defines an equivalent structure constant which has 4 indices. And if you raise the last index, you get this 4 tensor, and it has the property as this guy showed that it has to be antisymmetric, right? Totally antisymmetric. So that's very nice because now we have an object which is a color factor, sort of, but which doesn't satisfy the properties that I listed here. It doesn't satisfy, well, it doesn't, it's additional, it's slightly different, I should say. It's not, for example, a 3-term identity, Jacobi relation, but there's a 4-term identity. So this is called the fundamental which is just schematically, just take 4 of these guys, and you get 0 if you appropriately contract the indices. And Bagheer, Hay, and McLaughlin, they drew the similar kind of diagrams that I drew here, but in the case, these are 4-point vertices. So let me draw the diagram. So this identity can be translated to a diagrammatic notation as this diagram is equal to the sum of this diagram plus this diagram and the third diagram. So they call it the S-channel diagram, T-channel diagram, U-channel diagram, and V-channel diagram. And yes, so what happens here is that so similar to the what I had on the blackboard before is that you should think of amplitude in the Bagher-Lemon-Gustafson theory as being some sort of sum over quartic diagrams, Ni Ci over denominator I. And now in this case, well, first of all, there's a total antisymmetry, but more importantly, there is this Jacobi relation. So Ns is equal to Nt plus Nu plus Nv, and the same for Carla, of course. Sorry. And that's a non-trivial statement, just as for Yang-Mills theory, this is a non-trivial statement, so it has to be checked. And that's what they did. And remarkably, they get it to work. So they get it to work at 4 points. Well, 4 points is kind of easy, but it's a very non-trivial case to work at 6 points. At 4 points, there's no fundamental identity you can check. So the first case where you have a fundamental identity is 6 points. So they got it to work, and more remarkable, so they also get, similarly to the story here, they get amplitude relations out of this, which I erased. And moreover, then they consider what happens when you when you construct a double copy. What is this object? Well, it turns out to be gravity again. And not just any gravity, but the known gravity. So it's n equals 16 E88 gravity, which is written first down by Marcus and Schwartz in 1983, I believe. Yeah, so that's quite remarkable that starting from this, well, from my point of view, exotic theory, and then massaging it into that form and then squaring it, you get this theory from 1983, which was quite an exciting story. Okay. What? Yeah, well, I don't know.
Sorry.
Yeah, sorry. Yeah. So one reason why I talked about this example is because it gives a new manifestations, so to speak, of the duality, which doesn't involve cubic vertices, but instead it involves quartic vertices. So given this, you can start wondering, well, what happens to other color structures which can also appear in amplitudes? It's fairly well known that at one loop level, in effective action, you start seeing color factors which are not of FABC, even in Yang-Mills theory. So, for example, you start seeing totally symmetric color factors. So D, A, B, C, D, and so on. So totally symmetric. Okay, so what about these guys? Do we know anything about them? Do we know whether there's a dual kinematical expressions which somehow has the same properties? Well, we don't know so much, but there is some partial understanding. And in particular, I want to point out this paper by Carlos Mafra from last week and Slaughter. They have some very nice formulas for the string theory integrand at one loop level, and they.
Is this all in 4 dimensions? Gravity is.
Oh, so okay, I didn't say that actually. Yeah, so that's a good point. This is actually, it's supposed to be any dimension, so it's not depending on the 4-dimensional properties. And we checked that in some cases. We checked it, for example, by computing loop amplitudes in higher dimensions, and check that they have the right unitarity cuts and so on. So yeah, I should also mention that what's proven and what's not proven. I have neglected that. So at tree level, the fact that you can write the amplitude on this form, well, for the Yang-Mills theory, not for the BLG theory, has been proven. So that has been proven in various indirect ways. For example, you can say that amplitude relations. Well, that shows at least that the consequences of this representation is true. But there's also explicit solutions to the numerators, which, for example, just inverts the numerators in terms of partial trees. And this inversion is valid in any dimension. Well, at least so it's claimed, and so it looks like it's in any dimension. Yeah.
My question was for this particularly d equal to 4 super Yang-Mills. So the gravity theory are also are four-dimensional, or they could be.
Oh, it should work in any dimension, as far as I know. It's actually happier to live in higher dimensions, or to live in general dimensions, than to live in any specific dimension, because, well, for example, at loop level, what you do is that you encounter, for example, at one loop level, you encounter diagrams which are, for example, pentagons, and so on, and in four-dimensional theories, we know that this all reduces to boxes. I don't know if you're aware of that, but in four-dimensional amplitudes, we usually say that, well, this reduced to boxes, so they're not needed. But in this way of thinking of it, I want to have cubic diagrams, and cubic diagrams are the natural building blocks in the dimensions, actually. So, yeah, I think the d-dimensional properties are pretty safe. I will shortly talk about loop level, and there much less is known. Okay, so I just wanna, so this is from this year, or from last week actually. So I don't want to say too much, but what they did here is that, for example, they wrote up things which were f to the 4 amplitudes, and they considered a case where you could actually write this as NICI over DI, and although they have very interesting formulas, yes, still the numerator is not quite known, except there is one case where it's known, and that's something I will mention in about 10 minutes. So I should say, so in this case, well, in this case you can consider that, well, there is an effective action which has the form of this. So there's f to the 4. This is something you get in string theory, and then it turns out that it should multiply some DABC structure constant. I'm being a bit schematic here. Of course, this indices has to be contracted to the gauge fields and so on. And then this is actually alpha prime squared. But they considered this kind of object, which is naturally occurs in the one loop amplitude in string theory, and they from that they got expression that looks like this. So they were wondering whether so this color factors actually also satisfy four-term identities like this, which is something that you can see from, for example, if you have a D, A, B, C, D contracted into F, E, F, A, and then you, let's see if I can get it right. If you symmetrize these indices, this is 0. So that's a generalized Jacobi identity. And in terms of color factor, it looks like this. So they were asking the question whether you can find object that looks like this as well. And yeah, not so much is known about this case, but there is actually one example of it. And I will show you that actually in 10 minutes, because before that I have to actually explain how that example was calculated, because this is a loop level example actually. So let me get back to that. Hopefully I won't erase it. So let me talk about loop level now. And so one thing to note is that this way of writing the amplitude as numerator, color factor over denominator, That's quite reminiscent of how Feynman diagrams work, and it's quite reminiscent of how unitarity method works, for example, to construct loop amplitudes. They also get amplitudes on this form. Of course, at loop level, you also have an integration. So that's something we were aware of, that this way of writing loop amplitudes, this way of writing amplitudes is generally well suited to do loop computations. So so we suspected from the right beginning that it should generalize to loop level, but we didn't have any evidence of it because it's actually a non-trivial statement that it generates to loop level. But in 2010, the second paper, we did find example of this. So then, since we had one example, then we immediately generalized and said, well, then it's probably true to all loops. So here's how it looks like. So you don't have to change much. Okay, so let me just write this. Okay, so at loop level, the amplitude is going to look like this. It's still going to be kinematics times color, and it's going to be denominator. And there's a sum here over the diagrams. It still is going to be cubic. So this is Yang-Mills theory. And now you have integration measure and so on. And there also needs to be a symmetry factor, because sometimes you can encounter diagrams. For example, if you encounter diagrams like this has to have a symmetry factor, and that's not included in the numerator. But okay, so one important difference between loop level and tree level is that you have to worry about the dependence of loop momentum, because this is at the integrand. So this is before integration. So that's our claim, that it works before integration. But what happens after integration, we don't know. We don't know what properties survives after integration. Of course, if the numerator happened to be independent loop momentum, then the properties just goes on the outside of the integral, and everything works very well. And there's a few examples of that. But in general, there will be some loop momentum dependence, and you have to think about it carefully, because now you will have Jacobi relations. Which, well, they look the same. But there's a loop momentum dependence here. And let me just put plus minus again, because I'm a bit ambiguous about what sign is. Of course, you could say that, well, at tree level, the numerator also depends on kinematics, so what's the difference? Well, the difference is that the loop momentum is not perfectly well defined. You can shift it and so on. So you have to treat it much more carefully. But if you treat it carefully, it works. Let me draw some figures here. So here's a tree loop diagram, and what we managed to find a numerator of this diagram, which can be expressed as a difference of this diagram minus that diagram, for example. So that's just one of the Jacobi relations that we found in this paper from 2010. There's lots of them, of course, but here's just an example. So So this is the relation for the numerators. And now, okay, what do you do with the loop momentum? Well, you have to line it up appropriately. So you have to line up the loop momentum in each integral. So this is L1, say, and you call this, for example, L2, 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 and here's L3, L3, L3. And so essentially, these diagrams are they're almost the same for each internal edge, except for around this area here. So in this region here, the diagrams are different, right? And so here you can see that here is actually we have inserted a Jacobi relation, and that's why these diagrams are related. And one curious feature here is, which becomes really apparent at loop level, is that this is a non-planar diagram, and it's written as a difference of planar. Right. So, and this is a general feature that appears in all cases. We know that you can always write the planar diagrams as a difference of planar ones.
For the gravity?
Yes, but it's not. It can't be just any representation of the planar. It has to be a very specific representation of the planar diagrams. So, for example, you cannot use dual conformal diagrams in Yang-Mills. You have to use very specific numerators for this diagram, such that all the Jacobi relations are satisfied. And once you have that, then you can get gravity, of course. So unfortunately, even though I'm telling you that this is you're getting all the non-planar for free, unfortunately, given that we know a lot about planar, we know planar diagrams. For example, at 4 points, the planar diagram is written down all the way to 7 loops, I think, by Mark Spallin and company. We can't just feed it in. It doesn't work. You have to do some rearrangement, which is quite non-trivial. So yeah, there's some technical difficulty in just taking the amplitude from the literature and getting the non-planar. So instead, you have to do a rearrangement, and when you get to sufficiently high loop order, this rearrangement becomes very non-trivial. So, yeah. So what? Sorry, 2 loops.
For the 2 loop n equal 8 supergravity thing, have you managed to
4 point, you mean?
Yeah, 4 point. Yes.
Okay. Yeah. So the reason why I show you 3 loop is because 4 point, 1 loop and 2 loop is kind of trivial. But I will actually mention that in a second. Yeah, if you wait. So yeah, I should also say then, once you have reorganized your Yang-Mills amplitude such that these relations are satisfied, then you get gravity. So then you get the dual copy. Which is just, the same as that. I don't know if I want to write down the whole thing. Ni over di. And it could be different numerators. And of course, there's an integration. Well, I'm just going to write it like that. It's the same formula, except you have replaced the color factor for another numerator. And that's actually one reason why we write the color factor under the integration sign, because when you make this swap, the color factor better be under the integration, because it's going to depend on loop momentum. Okay, so let me come back to your question about 4.2 loop and also about 1 loop. So by good fortune, these amplitudes have been known for quite a long time, and they're actually on the right form that we want them to be. So the 1 loop, n equals 4. At 4 points, it's just a sum over box diagrams. And in this case, I'm not. What I mean here is, I mean the full diagram, including a denominator, numerator, and color factor. So this is the amplitude, and this is an old result by Michael Green and Schwartz. And Brink. And they got this result from considering string amplitude and then taking the field theory limit. And okay, so what it should say is that there's a numerator here, and let me just denote it by this. The numerator of this box is equal to ST times the tree level amplitude. And it's in a specific color order like this. This numerator happens to be fully crossing symmetric, even though it doesn't look so. But this operator this numerator has full crossing symmetry. And what that means is that, for example, when you want to look at the triangle diagram like this, 1, 2, 3, 4, then you can, by Jacobi relation, you can say, well, this diagram better be equal to the difference. I don't know. Let's see if I can draw it better. Let me redraw it. Okay. So this diagram should be the difference. So the numerator of this diagram should be the difference of this guy minus that guy, where this is 2 and 1, so you swap 1 and 2. That's essentially what the Jacobi, if I insert a Jacobi relation here, then I get this relation. And since this object is fully crossing symmetric, this is actually 0. So that means that there's no triangles in the amplitude, which is of course consistent. Okay, thank you. It's consistent with the result, and that's also consistent with the no triangle property. Okay, so this amplitude was already on the manifest form, such that the color kinematics duality holds manifestly. So that was quite lucky. Okay, let's go to the two-loop case quickly.
So I can ask something.
Yeah.
So here in the picture, you mean the diagrams mean propagators and also.
Okay, so here I just mean the numerator. Sorry.
Only numerators.
Only numerators. Yeah. Yeah, I should have used different colors, but okay. Okay, so the two-loop case is equal to the permutation of this double box and the crossed double box. And in this case, the numerators for both of them is equal to the same object. And it's equal to, it's almost the same as at one loop. So it's S and then it's ST A3. And this numerator satisfies all the desired Jacobi relations and so on. And since it does that, you expect that when you square these numerators, you get the n equals 8 supergravity amplitude. And that's of course well known, going back to the result of Michael Green and company, that gravity amplitude was actually just squaring the prefactor of this diagram. And similarly, this calculation, which was done by Byrne, Dixon, Dunbar, Polstein, and Rosowski, you just square this numerator, you get the gravity amplitude. So that's been well known already since the beginning when the calculations were done. What was not known was that this happened because there is secret Jacobi relations. Although it's kind of trivial in these cases because all it does is says that this is totally symmetric. But nonetheless, they're there. Okay, so I think in the last few minutes, if I have a few more minutes, I want to discuss 5 points a little bit. So I think I'm only going to have time to discuss 5.1 loop, but this is interesting enough. So here is a sketch of the calculation one loop. Okay, so first step, so this is the way it was done, and perhaps it's not the most efficient way, but it's the only way I kind of know how to do it. So first of all, I should say that generally at loop level you will get equations which are quite non-trivial because it relates the numerators at different points on the integrand phase space. So what you get is something which looks like functional equations. And the best way to solve functional equations is to write down an ansatz. So that's what we're going to do. So we're going to assume that the amplitude has this form. So this is n equals 4 Zupiag-Mills, and it's one loop. So we're going to assume that it's a sum over some permutations of two kinds of diagrams. So it's a box diagram, which has an external propagator, and it's a pentagon diagram, like this. You can also add triangles and bubbles and so on, but you probably don't want to add bubbles because that would destroy the UV properties of this theory. And you probably don't want to add triangles either because that's also is inconsistent with UV properties, and moreover it's inconsistent with the no triangle property of n equals 4. So this is our ansatz, and this actually turned out to be a sufficient ansatz. But of course we also need to write down what the numerators are. So this is also part of the ansatz. So here the numerator of the pentagon is equal to, well we're going to write some ansatz which captures the dependence of the loop momentum, but remains ambiguous about the dependence of the external momentum. So we're just going to call, there's a piece which is independent of loop momentum. I'm just going to call it beta 1, 2, 3, 4, 5. And then there's pieces which depend on loop momentum. And for example, there could be a piece which is linear in the loop momentum. But if it's linear at one loop, you can always square it and you get something which is quadratic. So instead I'm going to write something which is quadratic. So L1, so it says, let me just call this L1. Let's call this L2, L3, L4, L5, and let's call this 1, 2, 3, 4, 5. Okay, so it's a bit redundant parameterization, but it makes it simpler. So there's something which depends on L1 squared, and it has a coefficient which I call alpha 1, 2, 3, 4, 5. And now, in addition to imposing Jacobi relations and so on later on, I will also impose that this object has the dihedral symmetry that it seems to have. So this has the symmetry under cyclic rotations, right, and also under flip. So here you have to add the cyclic orbit of this term, just to make the symmetry manifest. Moreover, let me write down a numerator for the box. So in this case, okay, so I could have added things which are quadratic or quartic, something like that. But you can see that if you put something on like this on top of this integral, you get triangles. So you probably don't need these terms, because that would violate the assumption that there is no triangles, or the no triangle property in general. So let's just keep the answer simple like this. And then similarly, for the box, you write down something which is independent of loop momentum, but you still remain ambiguous about what it is. And then you can start adding stuff which depend on loop momentum. But then again, you can say, well, if you put something linear there, you can square it, and then you will cancel a propagator, and you will get a triangle. So you probably better not put anything. So that's my ansatz. And if you wanted, you could also put in numerators of triangles, but they are just 0. Okay, so that's ansatz. Now let's try to solve it. And of course, I won't have time to explain how to solve it, but essentially you write down you write down Jacobi relations. For example, here's one Jacobi relation, which says that this one has to be the difference of this diagram. Well, this is 1, 2. This is 1, 2, and then minus 2, 1. So basically, you commute leg 1 and 2. This is 3, 4, 5. 3, 4, 5. And here it's important you line up the momentum. So there's momentum there, loop momentum like this. So that's one relation you can write down. Another relation is that, well, there's a triangle and looks like this. But this is 0, of course, because we know triangles are 0. But this triangle should be the difference of this box minus this box, where I just so this is 3 and 4, so I just swap 3 and 4 here. And this is 0, so that means that this box is symmetric in 3 and 4. And by symmetry, you can also say that well, then it's symmetric in 4 and 5, and it's totally symmetric in all legs which connects to the box. So what you can state from this is that, well, whatever gamma is, it better be symmetric in the last 3 entries. That just follows from the absence of triangles. Moreover, because it has a vertex here, when you interchange, because it has a 3-point vertex here, and when you interchange 1 and 2, you get the minus the same diagram, so it better be antisymmetric, for example, in 1 and 2. Yeah, it better be antisymmetric in 1 and 2. And so on. And moreover, I don't know if do I have a minute or?
You might have 1.
1 minute, okay. So what you can do is you can drop dependence on the last 3 arguments because they're kind of redundant. All you have to do is keep track of the first 2 indices. So there's this object here, and I can in fact write down what it is. So I'm gonna skip the calculation. The calculation is that you have to impose the unitarity cuts. And then at the end of the day, when you do that, you get the explicit value for this guy, which is this delta 8q, which is supermomentum, and this has a 1, 2, and then 3, 4, 5, 3. I don't know if you can see that, and then it's over a Levi-Civita contraction of 1, 2, 3, 4. That turns out to be the solution when you impose Jacobi relations and you impose the unitarity cuts. And similarly, you can also write down beta on a very similar form. And in fact, what happens is that my alpha parameters get set to be 0. Okay, now in the last minute, I want to come back to this formula, which is relation for color factors which involves a DABCD. So you notice here that this gamma has some interesting properties. It has something which is totally symmetric and it has an antisymmetry. So in fact, gamma is actually dual to this object. So that's the case that we know of. And I should say, so it's A. Let me do it like this: F A1, A2, beta, or B, and then D, B, A1, A3, A2, A4, 5. So you know that this object gamma 1, 2 has the same symmetry properties and I can put 3 and 4 and 5 here and so on. But this object has the same symmetry properties of this object, and in fact, that's a good reason why it has so. Because if you construct object, let me just call this C12. So if you construct an amplitude which looks like gamma 1, 2, and then C12, like this here, and then S12, and then you sum over the permutation, then this happens to be equal to the UV divergence in 8 dimensions. D equals 8, so the analytically continued amplitude like this. So, and in fact, this should be equal this should be equal to a counter term, right, which is f to the 4. So yeah, that's the last thing I wanted to say. So that's the example where we have an object which actually satisfies such kind of relations, which is dual to color, and in fact it does produce an amplitude, which is just well, either you can think of it as UV divergence. There's also an epsilon, 1 over epsilon, which I dropped, but that has to be cancelled by a counter term, so there's an amplitude corresponding to that. Okay, and okay, let me stop. Sorry.
Thank you.
Sorry for.
We have a couple of minutes before the reception if there are any questions.
I think how to get to the counter term.
Yeah, sorry, I was a bit quick. So once you have this amplitude, you can compute the UV divergence of it
Going in this.
in arbitrary dimension. So you look at the first one, and this turns out to be a scalar pentagon, and this is a scalar box. So the box diverges before the pentagon, and in fact it diverges in 8 dimensions. So you just compute the UV divergence of that, and that just gives you a 1 over epsilon times a number. But it does give you, what it does give you is that it gives you gamma and over S, because that's manifest. It has a 1 over S, 1, 2 pole, and it has a gamma in the numerator. So this is if you do it carefully, you get this UV divergence.
How can the left-hand side diverge and not the right?
Which is right and left? Oh, here. No, because this is a relation on the numerator.
I'm sorry.
This is the numerators, yeah. Sorry.
But, so you got counter term which involves this structure constant.
Yeah. So it involves a structure constant which is DABCD. This is something that Carlos and company clarified to me actually. So, but so you get this structure, and that's an example where you have a more generalized situation, a more generalized Jacobi relation.
Can you perform a calculation of a loop amplitude only using BCJ and without any reference to unitary cuts?
Well, in hindsight, you could reproduce this calculations if you assume that there's no triangles and so on. Then you get the full amplitude up to 1 unfixed normalization. If you try to do the same thing at 3 loops, there's 3 unknown parameters. So that has to require 1 unitary to cut to fix those.
Okay, thank you again. I believe the reception